Now this I love. Okay. This, remember I was talking about the knee. I wasn't quite sure what was going on at the knee. I was pretty sure that this big actuator you see backing here actuates the knee. And here you see this here and that here. That I believe are the anchor points for the two actuators that we might be able to see a little bit from here that go up and do the flexion and the actuation. Now, I'm really surprised at the size of the knee one because I would think the flexion would be more important. And you're seeing this is the linear actuator. It's a really long actuator. It's pretty big. And this is the roller screw. So right there, you can see the roller screw coming out, and you can see the actuator actually spinning. So it's spinning and is causing that linkage to extend out, and that's what's causing the knee to move. Okay, so basically, it's retracting at this point. It's pulling that whole thing in. So it's rotation such that that length is getting shorter and shorter, and you can see where that knee mechanism is connected right there. So you can see how that's so it looks like I mean, that's the whole thing is all motors spin. And a linear actuator is taking rotary motion and converting it into linear motion. And that's how, yeah. And the way it works is it works just like a screw. So now you can see how it works. So is that now pretty clear, at least for the pitch? You'll see that rod pushes down, rotates about there, and that's how you get your pitch. They're not showing the yaw that's in there. And you see right here, this is a linear actuator that goes all the way down to the waist. So that's like, man, that's one big actuator. so, so that thing's got a lot of heft, and then got probably one on the other side. Notice that the shoulder has an anhedral angle. We haven't got into shoulders yet, but we're going to see that this angle is a very important angle, and that I think that the only one I've seen going anhedral. They should be going dihedral.
Hi, I'm for anyone. I can do more than you think. Scan complete. And you, what do you want me to do?
Wow. They are interesting. Okay. So this is Neura with their 4NE1. It's actually pronounced for anyone bot. And this is, and what kind of intrigued me when I looked at it is there anything interesting about what you just see from this image? Now, this is actually a CGI image, but it is very close to the real bot. And there was one thing that, two things that kind of jumped out at me. What did you, in anything that you notice?
I think the hand, the elbow jaw is quite high, a little bit different, the elbow. And I also think the hip is strange. It's like
Yeah, yeah. So the first thing was, I was like, "Oh, darn it," just like 1X, we have no idea what the hip is. And so I was like, "Oh, what kind of hip is it? Is it a far hip? What is it? Are they using the same thing?" But it's so neatly covered up there, we can't tell. I wasn't sure if they even have a waist or not. I mean, they could, but the other thing is like, wait a minute, that wrist, that is such a compact wrist. No way. No, this is just CGI. But the thing that really made me go crazy is that I said, wait a minute, they may not have 3 degrees of freedom up here. They might have like an AF or no, it's you know uh, and the because look right down here. You see that line right there? If I'm not mistaken, that means they have rotation there. It looks to me like they're rotating below the knee. Like nobody rotates below the. You remember I said that's toxic. You don't need that. Why is that there? And if you're putting it there, it means you don't need the rotation up here. So that's what I'm thinking. Oh, they probably had. So maybe that's a. So these are like the conclude. It's like conclusions I jumped to. Okay, so I was jumping to conclusions here. So I've got to sort this thing out and kind of what's going on because I it was a head scratcher. And again, I'm wondering, oh, this wrist. There's no way they have 3 degrees of freedom here. They might be using the redundancy that you have up here in the shoulder for that, so they could get away with, having such a, a wrist that, look at that. That is a very slender wrist. It's the most slender that we've seen. It's like, all right, how are they pulling this off? So,
Why do they displaced?
here's like
Do you
another
think
image.
using abduction flexion in the hip and this rotation beneath the knee?
Oh, I'm solving. Don't worry, don't worry. We're gonna uncover the mystery because it's great. It's great. So, looking here is another CGI to get an idea that their speed is not that impressive. 3 kilometers per hour is not 3 miles per hour. Okay, it's not quite 2 miles per hour. If they could do that, and it's just like a little bit below of where we would like it to be for being able to do useful work in the factory. So I don't know if that's their target or if they can actually do that. But again, looking here, we can't get enough about what's going down here in the legs. It's a computer rendering. But when I look here, I'm not seeing anything that indicates rotation about the leg. I mean, you could see this here. That's just a cover plate coming off. It's like between here and there, you see nothing that would indicate that the leg can rotate. So they must be doing it all down there. So, still a six off leg. It's just that they reorganize everything from one leg. So it's okay. It might be different. We could see it. The wrist rotates here, but we're not quite sure what's going on there. Again, from this, we can't really glean anything, and this is not conclusive evidence of anything yet. So I found this image, and like one was like, "Oh, cool! I can see something all of a sudden." So sure enough, they have a waist. You could see the waist in here, and you can see the linear actuators that are in here, and you can see the carton joint that's here, and you can see the rotation. So they have a 3 degree of freedom waist here. So they would have what's a ZXY, a Z dash XY waist is what's there. I can't see enough of what's going on here in the hip because the table gets in the way. Like, and I'm not quite sure what Matthew Broderick is doing in the image. So, okay, so we got this image here. Are there any better images? The other thing we could see is like, look, they got a camera suite right down here. I assume there's one up in the head. We can kind of see that. There was this line. It's like I can't believe they showed it without its soft covering, and you can begin to see something. And it's very hard to tease out, very very hard to tease out. And so again, we get a much better view of the waist up here, but you can see here, um, we can see what are the rotary actuators. So this is their R, and you'll see it has an angle. I'm not sure whether that's a kind of an angle, yeah. Um, and because but it's the rotary axis, not the flexure, so it's really weird. So you get the rotation coming down here. And you have this thing here, which is like it looks like a huge yoke, and I'm not quite sure. It's so big, it's suggestive that that point there must be where the abduction happens. And you would think because it's so big that there's probably a rotary actuator right in there. But I think you would be wrong because I'm seeing these connecting rods over there. And I think this is just a big carton joint that we can't see enough. And something is going on down here for the flexion. So I'm not getting enough to completely tease out the mechanism, but I think it's sort of what we've already seen in Apollo, and we definitely saw it in the G-Peng iron robot, that they have two linear actuators in here to do the trick of flexion and abduction. That's what they're now this big massive thing here, this looks like they have a huge servo in there. My suspicion is that's for the knee. That was my first suspicion, and it looks like I'm right. The other thing is we're gonna see some interesting things here about the wrists that are gonna come through. So they're doing something here, and again, I'm not getting a clear enough impression, but however they did it, it is very
So it's
compact.
nice.
Very oh, it's this is German engineering, okay? And so they're based just south of Stuttgart, and I think it's Metzlingen, and it's known as that's where the Hugo Boss factory outlet is. So if if you're looking for it's the Hugo Boss up there, yes.
Design. This is ref, right?
Uh, okay, I think it is. R, it's yes, it's the RAF that we've talked about, R dash AF, which is what Apollo and 1X is. So if I was to put it on the graph, it would be over there. So it's a kind of RAF, but it's got the parallel mechanism. It's not RAF, R dash A dash F, but it's definitely R dash AF. And so that's a pretty interesting. I'm hoping to find more evidence of exactly that, but it seems to be very compact to what we've seen of the others. But they seem to be using a lot of linear actuators that we can kind of see. So continuing on through here, a glimpse at the hand. Couldn't see very much in the hand, but it looks to me like they have only they drop one of the IP joints. So you have the pip, but you don't have the dip. So out here they have it kind of pre-rotated there. The question is whether they're using tendons or not. I think I know the answer to that, but we'll get to it a little bit further on. But here is also like a quick glimpse of the interior of the torso, and you see right here, this is a linear actuator. It goes all the way down to the waist. So that's like, man, that's one big actuator. so, so that thing's got a lot of heft, and they got probably one on the other side. First, I wasn't sure if they were using that for something else, but it looks like they have whoops rotary actuators up here for the shoulders. So I don't think it has any to show. But then I noticed right here, oh, there's a camera suite right on the side as well. So they have this camera here, they have that camera here. They seem to have a lot of cameras pointing right. And of course, we can see here they've got downward facing camera. They have cameras over here on the left and right that we get an idea. Now, this is the one part that I guess surprised me, and that is notice that the shoulder has an anhedral angle. We haven't got into shoulders yet, but we're going to see that this angle is a very important angle, and that I think they're the only one I've seen going anhedral. They should be going dihedral. A lot of shoulders are actually neutral. They come straight across. And this comes down to singularities. And what that means is that if you start working up with your arm around here, you're going to have these singularity issues of things flipping around. It doesn't mean you can't work up high. It's just that you have to get yourself around that singularity some way. And it means that it would almost prefer to always work low below that level. And then once you get up around that plane, it's a bit tricky. So it's not the choice I would have made. And that's one of those things that I would love to talk to one of their engineers, perhaps David, to find out. It's like, oh, okay, why that? Why didn't you go the other way with it? And it may be that they just feel that, oh, they can conquer it with software. There is a way to get around there that it may or may not be important. And it may be that it gives them almost a more human appearance, you could say, as far as like the shoulder blades and everything else that are coming on down. I'm not sure how big the battery pack is, because with all the stuff that was in that torso, I'm not sure there's any room for batteries. Okay. This here was see. Oh, there's a back camera too, so we could see the side camera. So they've got camera. I think all the others do. The others is more or less just like one camera in the head. The original Tesla design was putting it in there, and then they kind of scale back and just kind of put one in the head, because every one of these things requires compute. So at first, the feeling was that you would just have your bot littered with sensors all over the place, and you put it in places where they wouldn't be blocked. And most everyone is saying no, no, we'll just go with one, because that's CP. There's a lot of compute and synthesizing all these images and stuff like that. So I don't see, they probably have their own reason. And it looks like, it's kind of I think an off the shelf kind of sensor that's very common in a lot of mobile robots. So, and the other thing you point out with this company is that they've been around since 2019, and they didn't start building humanoid bots. They started building mobile robots and cobots. They have tons of experience in the cobotic field. They have cobots that are working in factories today, and cobots are designed to be around humans and not hurt them. And they know a lot about actuators and stuff like that. So they are probably like the only, pure robot company that decided to start building a humanoid bot. I'm still waiting for, the ABBs, the Kukas, and the Fanics of the world to get involved in the humanoid bot space, because they're coming from that. And it may be they're coming from too much of an industrial robot space and not a cobot space. So this is like a natural pivot. Is like if you have a lot of expertise in that area already, I think they can do a pretty. So again, they work a lot in mobile robots and know a lot about navigation, and so that's probably why they're comfortable with these suites and believe that they can handle it. So we can get a little bit of an idea of what it looks like there, and some more. Now here you can just see the hand. You see the clasp. I put this in here because you can see how the hand is closed there, because of one IP joint there. It doesn't curl all the way around the way we would be
It
used to.
doesn't seem a good hand at
Then
all. This is not a good hand.
it's an okay hand, considering that. Right? There's so much to a humanoid bot, but you can't get it all right. And it's not bad for starters. And it seems like they're doing a lot of tasks with it already that may be sufficient. The other thing I noticed is that it really stands tall. It stands really quite tall. It's about 5'11", and for a German humanoid bot company, I'm not surprised, because the German population tends to be demographically a little bit taller, like the average human, and so it would fit in a bit more, being closer to probably what is the average male, uh, in Germany. And just looking at it, it's like, oh wow, look, its knees are straight, absolutely straight here. So that's rather interesting to notice. Now this I love. Okay, this remember I was talking about the knee. I wasn't quite sure what was going on at the knee. I was pretty sure that this big actuator you see backing here actuates the knee. And here you see this here and that here. That I believe are the anchor points for the two actuators that we might be able to see a little bit through here that go up and do the flexion and the actuation. Now, I'm really surprised at the size of the knee one, because I would think the flexion would be more important. And I'm not sure that even with the two of those, you can get as much oomph out of those as you would with this. I could be wrong, but just look at the grandiosity and size of that thing. And this is just beautiful. You're going to love this. Yeah. So let's look at that. You can see it rotating. You
I
see
just
it?
want to understand. You say this is barrel mechanism to do the flexion and abduction. So what does the rotation is doing here?
Well, this here is this is the knee joint. And you're seeing this is the linear actuator. It's a really long actuator. It's pretty big. And this is the roller screw. So right there, you can see the roller screw coming out, and you can see the actuator actually spinning. So it's spinning and is causing that linkage to extend out, and that's what's causing the knee to move. Okay, so basically, it's retracting at this point. It's pulling that whole thing in. So it's rotation such that that length is getting shorter and shorter, and you can see where that knee mechanism is connected right there. So you can see how that's so it looks like I mean, that's the whole thing is all motors spin. And a linear actuator is taking rotary motion and converting it into linear motion. And that's how yeah, and the way it works is it works just like a screw. So if you put a screw in a board and then you start to take a screwdriver and spin it, as you're rotating that screw, you're going to notice it translates forward till it goes into the wall. And then if you counter rotate it, you'll notice it comes out. And because that thread allows it to move in and then to come back out. And that's exactly what's going on here is that in order, and the reason why the thing is so long is because you have this very long rod that's inside of there that has the thread along there, which is the screw, and it's a roller screw. And usually have ball bearings along there to reduce the friction. And think of the motor as basically being a nut on a somewhere. Oh, yeah, here we go. Ooh, props. Okay. I've got the kind of a prop here is that you see, if I spin my nut, you see how the nut moves along there. But if I somehow have the nut spin this way, but keep it in the same position, it's going to cause this bolt to move, right? So as this nut is spinning around, and if I'm not, instead of turning uh, yeah, I think you get the idea. Is that spinning motor is going to end up causing that rod to extend out, that little linkage mechanism, which is then connected here to the knee, which makes it move. And it has to be very long because they need to have a lot of travel. And if your motor is very short, then that means you don't have much travel before this thing falls off of the nut. And then so you need to make sure it's very long so that when you retract this all the way in, right? If I retract it all the way in, I've got to have my actuator be
I
like
understand that
to get
just
it in there.
quickly. The barrel actuators for the flexion abduction is not related to this part as well.
Correct. So it looks like they're in here somewhere. So what I think they have is they've got a big motor like this, and then they have two smaller ones up here. So they get a big one, and then somewhere up there, they've managed to fit it, and we can barely see like there's something up here, but we're not getting enough of a view. And that there is probably the anchor points for the ends of those two. And those anchor points are going to have to be some kind of Heim joint there or a spherical joint because the movement of those things, I think, goes in a couple different directions. But again, if you look at the overall packaging that's in there, and again, it's a little bit like a stormtrooper. These these plastic external parts here that kind of cover it up. And, as we go along and look at it, that normally is covered with fabric. And right here, for some reason, the fabric rolled up, and we get to see a little bit of what's going on. Again, these control rods are kind of going up to help with deflection. So they may not have worked out exactly how to cover this whole mechanism yet with it always slide.
But it
It's
seems
got to
what
be
I saw
complicated.
from you, it seems much better than what we haven't compared to other humanoids.
Yeah, yeah. Well, there's some interest. Yeah, from the way they've done that, seems to be really good. Now, this is a 3-bar mechanism they have here, as opposed to like the Hurkins joint that we talked about that Optimus is using and iron. And maybe that's why it has such a big actuator is because you have kind of these deadlock situations you have to be careful of. That as you get near 0 degrees or 180 degrees, you lose all mechanical advantage. And depending on your range of motion. So it may be that at some point for you to really need like a lot of force to be able to get the knee to kind of move the way they want. That could be the only reason because I don't see why the actuator diameter has to be so. I understand why it has to be long, but I don't quite see why the diameter has to be so big unless they really need to come up with a lot of power. But again, looking up here at the wrist, like they almost don't exist. You're looking at that, it's like that is just such a compact kind of wrist mechanism in there. It's amazing. Um, now, okay. Oh, that was like I didn't clip very well at the very end there. All right. So now let's take a look at the wrist. And so I was able to grab two images that they had in there of the wrist. And you can see right here, here are the two linkages that actually cause the move, just like in Apollo, just like in Optimus. That same idea that you have a cardan joint down here, what I think is a cardan joint, and they've got two linear actuators, much smaller linear actuators there that make these control rods go up and down. And we're going to see a video of this in a second, but these are kind of two glimpses. Um, Now, one of the things they did, so at first I thought, maybe they got rid of the wrist yaw, right? Because I wasn't sure how they made it so thin unless they did this actuation strategy. And you'll see that they've decided that for the pitch, they're not going to have like a, a huge range on the pitch. They got a pitch that emulates the human. So you see kind of the back direction doesn't go very far. Well, my hand really only goes this far back, but down it goes really far. And that's why you can see this cutaway here. It allows them to pitch a lot, which is rotating about this. The other thing that's interesting is that I think Optimus and Apollo have their card joint more in the center here, and they intentionally offset it there. And that offset makes sense if you want to have a range of motion which is non-symmetrical, that you're favoring one side over another. And that's sort of anatomically correct. That's why they put it there. So you can see this is where the pitch axis is. And I think they have like in here another joint which allows them to get the yawing motion that's going on in there. The other thing I want you to see is that this kind of mechanism just is very easy for your cabling. You don't need any external cabling. You see it, it just smoothly runs right into it because it is opened up. There's the other thing that amazed me is like I'm only seeing okay, this yellow wire, I'm not sure what it's doing. It kind of goes up and back around like that, but you got well, it looks like just three wires heading into the hand. Yeah, I'm expecting you like more. Maybe there are some other cables running. It was like, oh, there's not a whole lot of cabling left after that. Just goes right on in there for the hand. So they don't need to route very much, and you see they got plenty of space to be able to route any sort of cabling that you would need below that point. And right here we can see the actual point of where these connect onto the wrist to be able to give that lever arm and a much nicer view of it there. Again, that's kind of it has to be a Heim joint of some sort there for that mechanism to work correctly. Now, looking at this, my impression is like, okay, they probably don't have a whole lot of movement in yaw, but we will see. So now you can see how it works. So is that now pretty clear, at least for the pitch? You'll see that rod pushes down, rotates about there, and that's how you get your pitch. They're not showing the yaw that's in there, but I think we're going to see something in a second here. Okay, here's again a close up of the hand. Again, that wrist is just crazy thin. It's just so slender, and even the forearm is not very big. This is much more slender than the Optimus forearm, and they've managed to go ahead and fit those things in there. Another little view that we can see the opening in there, and we can also see a little bit of what the hand looks like. Most of the images that they showed of the hand were very blurry, so good, really good detail in a lot of them. Uh, and so here again, it looks like they've got probably different versions of the hand. This one's white, but this one I put in there. It says, "Oh, look, they do have decent yaw." So that was like more yaw out of that wrist than I expected. So I was finally able to get an image catching it in kind of the yawing motion there, which looks like might have something to do with. I'm not sure if that's probably not what the joint is. I don't think I was thinking of the joint. That might actually be data that they plug into. But we can see where the IP joints are. We can't really tell whether it's tendon based or not at this point. Again, this really blurry image of the hand where we can see. Yeah, so if you look at that, you'll see something going through here that is suggestive of like a tendon. The question is it really a tendon? And I think in these pictures, we get to see it a little bit more. So we can see how the thumb is done. We can see kind of these little points here, and that usually is an indicator they probably have a linkage that's built in there. And I could start to see a little bit here and then I think the next image, it's a bit more in focus. Yeah, you see that there? That's a metal rod that comes right. So they are using a linkage mechanism for the control the movement of the fingers. Now I don't think they have the abduction of the fingers. I think they only have the flexion extension. But I'm pretty sure we can say this is not tendon based. This is purely mechanical on their hand, what they're doing. And again, it only has one IP joint instead of both. So that's which may be good. I mean, we'll have to find out how much you can actually do with a hand of that kind of complexity or not. All right. Now, as far as walking, they did not really show it ever walking. It's always in standing position. This is a clip from a video they had where they quote showed it walking, but at like superhuman speeds. I mean, it just was like the time lapse was crazy. So it was just a blur going through. So it was like watching the flash just. And this was like only one incident that I could like stop the frame to see where it was in the movement. And so if that's their moving policy, walking policy, it looks like its legs are still bent, but it could be that this is the posture it takes to pick that thing up because the chances are I would be bending my knee to get down to that and not necessarily standing up straight. So it's hard to tell if it is able to keep its knees straight when walking. It can definitely be very straight when standing. We've seen that. So it was hard to tell. The main thing I wanted to figure out is like what's going down in the ankles. I don't, and this is like the only picture I've got of the feet and the ankles. And I tried to blow it up as best as possible. And I have a feeling since they've been,
It's quite strange foot.
yeah, it's hard to tell, but because they're leaning so much in with these linear actuators in many places in the wrist, in the waist, up here, I'm willing to bet that it's the same strategy on your cardan joint with two linear actuators for that Mimo kind of multi in, multi out parallel actuation. I'm pretty sure that's what they're doing, but again, it's too grainy at this point for me to say conclusively. But uh, yeah, there's never any guarantees, but let's say I'm 99% sure that that's exactly how it's actuated down there. And yeah, that's it. That's 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 a separate episode right there, I think. But
I think we should have the CEO, Neura, on the podcast.
it's fascinating. I mean, from the mechanical standpoint, it really is standing out. Is that they've done a lot of very interesting things. Um, the it's just so slender in so many places, and the actuation strategy in the hip uh, looks interesting. Um, how they did it. It seems to have been simplified a little bit from the others. So it's a different pod. It's one of those with a mix of linear and I'd sort of talk about the different schools of thought out there as far as actuation strategy. That you have one group that I say is up at the North Pole, which is just all rotational, and then the polar opposite, down the South Pole, those that are doing linear actuation, and that's Apollo, keeping uh, with iron, and then you have those, the one that at the equator, which is Optimus, and now it looks like it's kind of been joined by for anyone that it's also has a mix of the two in there that seems to be similar to the Optimus strategy is as well. So they're definitely worth looking. I, yeah, yeah. They're I mean, the first thing I need to apologize for not having, like, looked at them sooner when I was doing my other analyses out there where they are because, now we are seeing there's at least one other that's kind of, well, kind of an our strategy that stayed in there. So their their hip strategy is a little bit different. So the numbers have changed a little bit, and I think we can kind of call them a major player at this point. Looks like they have good funding that they raised I think 120 million euros. They have an order book of about a billion. Um, and now I don't know if that order book of a billion is like just for humanoids or for like all their bots. So it looks like they already have cash flow because they have this other line of robots that probably helps keep the organization going. I think 300 employees or something like that. So they're kind of past that startup phase. Yeah, the only question is what is their AI strategy, and it seems to be that they're working with NVIDIA and Isaacs and stuff like that. Because one of the videos that went out there, I think, was showing their connection with Omniverse. They also had something showing the Omniverse where there's some images that I didn't realize was actually like out of Omniverse, and then they showed the real. Like, aha, okay, I was able to see a slight difference in there. So they clearly, they're using NVIDIA to help them out a lot of it. Just not sure where they get the compute from and what other neural nets that they're using or how much is homegrown. But from the mechanics, I mean, it's your typical kind of solid German engineering that it's compact. It's remarkably compact. You could see these memes, people are showing like what a German robot would look like, and it would just look like it. I have like these really weird buttons and be really bulky and stuff like that. But you see in this case, they've done a really good job on the packaging. That's so
I see your eyes lit up when you say
yeah,
that German
yeah. I mean,
engineering.
there's reasons why German exports as much stuff as they do, and their stuff ain't cheap, and it just comes down to quality. I mean, it's like they know what the secret sauce is to make something that's not going to break and with extreme precision, and that just comes with this fanatical obsession with precision. The same in Switzerland, and also the engineering schools they have are just top notch, and it's a field that a lot of Germans like going into, to become a mechanical engineer, and it's by the time well, they changed it a little bit now because they went to the U.S. program with also having like the bachelor's and the master's, but it used to be when you went to a German university, by the time you graduated, you had what I felt was the equivalent of a master's degree in the U.S. And but the U.S. only recognized it as like a bachelor's degree, and I'm like, these guys were in school for 7 years. They weren't there for 4 years, and they were required to do projects and internships at companies and stuff like that. That was like all part of that thing. So by the time they get out, especially the German school system, the gymnasium goes to 19, not to 18. You used to, not anymore. You used to have a year of obligatory service in the military. So that was like, so I mean, you couldn't start your university until you're like 20, and then it would be like a 7-year program by the time you get out. So you're like 27 when you're graduating. And I guess at that term, it's like, well, wait a minute. It's like, you don't become a productive member of society until age 27. We're going to do something about that. And so then they looked at the American program and said, oh, they can start graduating at 12, in their 12th year. You don't need to have a 13th year. Yeah, you don't have to go, no more have the obligatory service. And so they're kind of cranking them out a little bit faster. But still, I think there's a lot to be said about the quality. Yeah, yeah. The other thing that Germany has that is they have a very, very good internship program. There's actually two schools that people go to, and there's the university, which would be equivalent to going to a university school, and then there's what they call the Real Technique, which in the U.S. it'd say, oh, that's like going to a community or tech school or something like that. For Germany, it's actually looking at it with a source of pride that it's like, and unfortunately, they kind of screen the kids almost too early an age. It's like, oh, this kid will never make it to university, and it goes more in the university track. And the other's like, oh, this guy's is just going to be a technician. But the Real School, it's not community college. I mean, you come out of there really knowing how to work with stuff and how to build stuff. And so you get that combination of some really good, solid engineers, and then people that know how to actually, use a hammer and a screwdriver and a bunch of other equipment. Yeah, you get stuff that's quality built and reliable, and that's something that's been lacking in the US, and I know they've been trying to do a similar kind of apprenticeship program in the US, but it doesn't exist. So, it's definitely a much better program that way when you think about the quality of technicians you're gonna produce.